what we see is something quite interesting. So as we know, as we go from the topological to the trivial phase, the gap actually goes to 0 and then gets bigger again. So as we go steadily from the topological to the critical point, the gap must go from a finite value to 0. This means that the surface state penetration depth should go to infinity at the critical point. Okay? So that means that what's really going on is that the surface state gets larger and larger in the z direction as you go from the topological phase to the critical point. That means that the fraction of surface state electrons sampling the surface gets smaller and smaller. And this leads to the effect that we see. Meaning the effective mass is given by how many surface state electrons actually see the distortion. And that magnitude gets smaller and smaller as you go towards the critical point. So what we are seeing indirectly is that the surface state penetration actually goes to infinity as you go from the topological to the critical point. Okay. So now that we've looked at the composition dependence, we're ready to look at the effects of strain. Strain is very interesting in condensed matter systems. As you know, we have a lot of different effects of strain. One of my favorite examples is strontium glutamate, where you can actually increase PC by a factor of 1.4 by straining the sample. You can enhance ferroelectricity, and here in graphene, you can see that this is in the presence of strain, you get these peaks. These are pseudo-Landau levels due to a pseudo-magnetic field. So in PCIs, Evelyn and Liang predicted that strain can actually have similar effects as in graphene. So it can do a few different things. Strain can actually move the position of the Dirac points in momentum space, and that's the same as giving rise to the same phenomena that gives rise to pseudomagnetic fields. So strain can give you a pseudomagnetic field, and therefore it can give you Landau levels. Okay? So there are many interesting reasons to study the effect of strain. One thing I just want to mention is, no matter what strain does, however it shifts the Dirac point, you can always write the effect of strain as giving rise to some kind of a gauge field, and you can see that as long as the curl of this A, meaning that the shift of the momentum space position is not uniform in real space, you will get a pseudomagnetic field due to strain. Okay, now let's look at the data. What we did was, to create strain, we grew thin films of lead telluride, tin telluride on lead selenide. Okay? Now it's been known from literature that by this thin film structure gives rise to a very interesting two-dimensional buccal structure, which is shown here. Look at this length scale. This is 200 angstroms. So these are actually big. It's a two-dimensional buckling on the surface of the material. So what we did was, we grew these films inside our chamber and then transferred it to the SPM. So this is the image I showed you before. This is what we used as our substrate. And then let's just ask, what do you expect to see when you grow these layers of tin telluride? So here's lead selenide, and let's say I start depositing tin telluride atoms. The lattice mismatch between the two is about 3%. So initially, when you deposit the atoms, the first layer of atoms will conform beautifully and it will be highly strained. But as you grow more and more layers, you'll get more and more dislocations built into the system. And these dislocations relieve the strain, okay? Until you get to a very thick layer where you have enough of a dislocation density that the DC strain is completely released, and all you're left with is AC strain. So here is less than a monolayer of thin telluride. You can see there are no dislocation scales. This is a very strained system. And then as you grow thicker layers, you get these lines of dislocation. This is how the system relieves strain. And then with more and more thickness, the network of dislocations gets more and more dense. And finally, at 40 monolayers, you get this structure where DC strain has been released, but then you have a buccal structure which encodes AC strain. And the AC strain is really interesting for two reasons. One is that this means that if the strain has any effect at all on the Dirac point, it's going to be inhomogeneous in space, which can give rise to pseudomagnetic fields. And the second thing is, we can actually compare the different regions and actually in situ see the effects of compressive, tensile, or uniaxial strain on the Dirac point. So this is what the surface looks like. If you zoom in, you'll see that each of these regions is very well, it has a good lattice, so these are good thin films. And now, let's see. The first thing we need to do is determine strain. So to do this, we go to each point in our topography and ask the question, how much is the atom, how far is the atom from what should be its ideal position? Once you know that, you know strain. Okay? So we use an algorithm called the Lawlor-Fujita algorithm to detect this. And now let's apply the algorithm to this topography, and this is the strain map. Okay, the strain is rather large. It's -2% in the blue regions and +2% in the red regions. Now we're going to use QPI, another technique to look at dispersion, to look at the effects of the strain on the Dirac electrons. Okay? So the way QPI works is you have an incoming wave of electrons or quasiparticles. They scatter off some scattering center, and in regions where they overlap with each other, they cause an interference pattern. The wavelength of the interference pattern gives you direct information on the momentum of the quasiparticle, and the energy is set by the STM voltage. So we know the momentum and we know the energy, and therefore we know the dispersion. Okay, so now let's use that to look at the GIDV map on this and look at the quasiparticle interference. And to do that, we're going to take a Fourier transform, 1 minute left, of this entire region. So let me just do that. That's going to be tough. Can I have 5 more minutes? Okay, thank you. Okay, so we're going to take a Fourier transform of the GIDV maps as a function of energy, and then we're going to ask the question, what is the effect of strain on the Dirac electron? So let me do that. This is the Fourier transform of the GIDV map. This is an autocorrelation of the Fermi surface, and basically, if you compare these two, you can see that we can capture many of the features of the autocorrelation of the Fermi surface in our Fourier transform. So I'm going to use this Fourier transform to characterize what happens to the electrons in momentum space as a function of energy. Okay? So what I'm going to do is I'm going to start from an energy close to the Dirac point, here's the Dirac point, and sweep energy, and look at these Fourier transforms, and ask the question, what happens to the Dirac electron? Okay, now, so here we go. So you can see that as we change energy in the entire field of view, these three vectors change in size, and from the magnitude of these few vectors, you can get the dispersion. So this is the change in the Q vector. You plot this as a function of energy, and you can get the dispersion. Now this is for the entire field of view. And what we can do is we can actually go to the strain region, create a mask based on strain, and do selective Fourier transform of the positively strained regions and the negatively strained. So that's what I'm going to do now. I'm going to create a mask and take selective Fourier transform.